Go with the chapter 8-9 homework review. Sorry this is coming at you a little bit late. I was flooded in and separated from my tablet yesterday, but we're reunited and able to record this video for your viewing pleasure. So this homework assignment was about the last part of chapter 8 and the first part of chapter 9. It was largely conceptual, so pretty much all the questions were concepts, and for that reason I'm going to be going over just about all the questions that I'll go over today are about are conceptual in nature, not anything to do with numerical calculations. Overall, our performance on this homework was not too bad. Average score was 9.9 out of 12, but there were a few questions which I'll go over today where we had success rates of 60% or less. Now I do apologize, there were a few questions on here that cover material that we haven't really gone over yet. Those should not have been on the homework assignment, to be frank, but they were there, but there weren't that many of them, so I will cover those on a later date, if we still have trouble with those at that time. But for now, I'm just going to go over things that we've already covered in class and that we still had a little bit of trouble with. And the first few that I'll go over, I'll deal with the kinetic molecular theory of gases. This is one of the last parts of Chapter 8 on gases. And this deals with the sort of atomic or molecular level picture of how gas particles behave and sort of rationalizes the ideal gas law and those macroscopic behaviors of gases. So the kinetic molecular theory deals a lot with the motion of gas particles, which is quantified by kinetic energy and by velocity. So in this problem here, the first one here, we're considering two 1-liter samples of gas, one hydrogen and one oxygen, both at 1 atmosphere and 25 Celsius. Which statement most accurately describes the gases? So here we're asked to compare kinetic energies and velocities, so we need to know the relationship between those and other properties of ideal gases. Now, as it turns out, the kinetic energy is a function of temperature only when it comes to those four main properties of gases, which are pressure, volume, number of moles, and temperature. Now, I should point out that's the average kinetic energy for 1 mole of gas. So we have this relationship, if you want to think about it mathematically. The average kinetic energy for a mole of gas is 3/2 RT. So it doesn't matter what the identity of the gas is, it doesn't matter what its volume is or its pressure, it's just dependent on temperature. And that's going to be the average kinetic energy. But we should also realize the equation for kinetic energy is 1/2 mv squared. If we're talking about an entire mole of mole of gas, is going to be the molar mass times the average speed squared. So when we're doing these types of comparisons, the two things we need to realize are at a given temperature, gases will have the same average kinetic energy, but that kinetic energy depends on mass and velocity. So the heavier the gas will be moving slower, and the lighter gas will be moving faster at a given temperature. Alright, so let's go through these answer choices then and see which one works out for us. So in choice A, the average kinetic energy of O2 is greater than H2. Okay, as we said, they're at the same temperature here, and as soon as we see they're at the same temperature, we should know they have the same average kinetic energy. So that one's choice A is wrong. Choice B is the same story, but at this time it says that O2 is less than H2, but in terms of kinetic energy they'll be equal. Okay, so choice C is that exact possibility. The average kinetic energy of the two is equal. Choice D talks about average molecular speed. So here it would say that the O2 is greater than that of the H2 molecules. O2 is heavier than H2. The molar mass of O2 is 32. The molar mass of H2 is 2. So at a given temperature with a given kinetic energy, O2 will be moving slower. Okay, so that one's going to be wrong as well, leaving choice D as our only answer choice. So this next problem was almost identical in terms of the concept. So here we have now 3 flasks, 5 liters. The volume doesn't really matter for this problem, as we'll see, and they're fitted with pressure gauges and small valves, each containing gas at 273 Kelvin. Now right away we think about the temperature, because that's what's going to influence kinetic energy and velocity, which is what we're asked about here. So flask A contains 4 grams of hydrogen, flask B contains 4 grams of helium, and flask C contains 8 grams of CH4. Compare the flasks in terms of this characteristic, which is average molecular kinetic energy. Well, we don't even have to think about this one that hard, because if the temperature is the same for all of them, which it is, the average molecular kinetic energy is the same. So again, that simple equation, average kinetic energy is 3/2 RT. It only depends on temperature, which means choice C is the only one that works out for us. We don't even need to do a comparison here. They're all going to be equal. So related to the concept of molecular speed then is a fusion. Okay, so in a fusion we're looking at the escape of a gas through a small opening. So the rate of a fusion is proportional to the average of the speed, which we call URMS. So the faster the gas is moving, the faster it will escape, the faster the rate. And so here we're looking for which of the following gases effuses most rapidly. So if we solve for velocity using the kinetic energy equation above, what we get is that the URMS is equal to radical 3 RT over the molar mass. So we saw this in class. And this says that the average speed is inversely proportional to molar mass, which we talked about earlier. So, if we assume that all these gases are at the same temperature, the one that's lighter is going to move faster, the one that's heavier is going to move slower. Now, part of this problem, and I suspect the reason why choice A was popular, is realizing the correct chemical formula for these gases, which we need to find the molar mass. So all we need to do here is compare the molar masses. The one that's the largest molar mass is going to effuse slowest, so we're looking for the one that has the smallest molar mass, which is going to effuse most rapidly. So nitrogen, remember, exists as N2. It's a diatomic gas. So the molar mass for N2 is 28 grams per mole. And same with oxygen. It exists as a diatomic gas as O2. The molar mass is 32. Hydrogen chloride is HCl. Molar mass is 36.5 grams per mole. Okay, so ammonia here, we have to remember the formula for this is NH3. The molar mass is 17. 1 nitrogen and 3 hydrogen. And then carbon monoxide, CO. The molar mass is 28 grams per mole. Alright, so we just need to find the one that's smaller. That's going to be the one that effuses most rapidly, and of these choices, ammonia is the smallest gas. So some of you picked nitrogen, and I suspect this because you thought it was just nitrogen by itself, nitrogen atoms, but remember that nitrogen gas is N2 in its most stable state. Alright, and then finally another problem with effusion, and here we're considering two 1 liter samples of gas, one H2 and one O2, both at 1 atmosphere and 25 degrees Celsius, and now we're comparing the time that it takes to effuse. So, sorry, that's a typo. Alright, so we're looking for the time that it takes to effuse. We're comparing H2 and O2. Now again, this comes down to, we can think about it mathematically or we can think about it conceptually or both. So as we talked about, the lighter gas effuses faster. That was what we were directly comparing in the last problem. So if it effuses faster, it's going to take a shorter amount of time. And then the one that effuses slower is going to take a longer amount of time. So if we're doing a fusion, O2 is going to be slower because it's a heavier gas than H2. And H2 is going to be faster, which means O2 is going to have the longer time. H2 is going to be the shorter time. Alright, so that's the concept. Mathematically, it comes out from this effusion equation. So the rate of H2 divided by the rate of O2, those are inversely related to the time that it takes to effuse. As I said, the faster the rate of effusion, the shorter the time, and vice versa. So what that means is that if we're writing this equation in terms of time, the ratio has to be switched, and then that's equal to this square root ratio of molar masses, so the molar mass of O2 divided by the molar mass of H2. Okay, so the two equations, whether you're talking about rate or time, have slightly different forms. You have to invert one side if you're going to compare times. And so for this reason, a lot of you, when we do numerical problems on this, also had a little bit of a trouble remembering that. But nevertheless, however you think about this, whether it's conceptually or mathematically, O2 is a higher molar mass. It's going to diffuse slower, which means it's going to take a longer amount of time. So the time for a given fraction of O2 to effuse is greater than the time that it takes for hydrogen. That would be choice A. Alright, so then one other thing with gases that we dealt with was real gases. And this is sort of the classic question we ask you, and I went over it in class and we still had a little bit of trouble with it. It just sort of have to remember the scenario and sort of remember why it is to help internalize it. So here we're looking for deviations from the ideal gas law. Okay, so no gas is perfectly ideal. Every gas is going to deviate, but under certain conditions they're going to behave more ideally than others. Okay, so they're going to behave most ideally under the following scenarios. Okay, so ideal gases, we assume they have very small particle volume. The particles are very far apart from each other, so that's going to occur at either low pressure or large volume, however the scenario is phrased. But if we have a low pressure or a very large volume, the gas molecules are very far apart from each other. They don't interact with each other as much. And then also, in terms of temperature, it's going to be the higher the temperature. So low pressure and large volume put the particles far away from each other, which allows them to behave more ideally. And then at high temperature, the particles are moving faster, as we talked about extensively earlier, and this also causes them to interact with each other less. Alright, so under these extremes, low pressure, large volume, high temperature, that's when the gases are going to behave most ideally. So here we're talking about temperature and pressure, so the one that's going to be where we're going to have the least deviations from ideal gas behavior are going to be high temperatures and low pressures. Okay? Alright, and then this one was a true-false question where we did slightly worse than if we would have just flipped a coin, so I want to go over this one a little bit. So atomic solids generally have low melting points. So we have to sort of keep in mind the differences between atomic and molecular solids. So atomic solids are, there's all metals, and then they include some nonmetals as well, or metalloids, boron, silicon, carbon are the big ones. So in atomic solids, the reason they exist as solids and not as gases as a lot of atomic compounds do, like the ideal gases, the reason they're solids is because they have very strong bonds holding them together in 3 dimensions. So metallic, metals, we have metallic bonding, and then in non-metal atomic solids like boron, silicon, carbon, we have sort of these network covalent bonds. So covalent bonds extending in all directions, an infinite sort of dimension, if you will, so they go out forever. And those are holding them together. So they're very strong intra-atomic forces of attraction holding everything together, which allows them to be solid. So these generally have high melting points. Now in contrast, most molecular solids have low melting points, because in this case they're held together by just intermolecular forces, which are much weaker than the bonds that hold together atomic solids. So pretty much any covalent compound could form a molecular solid if it were to exist in the solid state. Now some elements are molecular solids as well, so the ones that are diatomic, like I2 or tetratomic P4S8, these are molecular elements, and they exist as solids at room temperature, but they're held together very weakly by very weak dispersion forces, so they're going to have low melting points. So whatever type it is, they tend to have low melting points. Of course, if they have very large structures, they can have higher melting points than others, but typically they're going to be much lower than atomic solids, which include mostly metals. So atomic solids generally have low melting points. This should be false. Most of them have high melting points, like the metals in particular. Alright, and then finally this one is mislabeled in terms of the title. This is Intermolecular Forces. Anyway, the concept here is intermolecular forces, and we're looking for, in frozen methane, the molecules are held in place by. Alright, so we sort of want to think about a bit of a flow chart when deciding which intermolecular forces are strongest. So in problems like this, where we're looking for how are molecules held together in a condensed phase, we want to look for the strongest intermolecular force. That's going to be the one that dominates. And so we want to think about sort of a flow chart. So London dispersion forces we don't even have to think about. Now it's the weakest one, but all molecules have London dispersion forces holding them together. Okay, so it doesn't matter what it is, that's going to be a possibility. But then we want to think of, does it also have one of the other forces that's stronger? So then we go to the next strongest one, which is dipole-dipole. And for this to occur, the molecule must be polar. And then finally, the strongest of the three is hydrogen bonds, which is a special type of dipole-dipole force. And in this case, the molecule needs to have either OH, NH, or FH bonds. Okay, so if it doesn't have hydrogen bonded directly to one of those elements, it's not going to be hydrogen bonded. So going back to this problem, then we have CH4, which is methane. Okay, if we draw the structure for that, it's tetrahedral. There are no lone pairs. And just like any AXM structure with no lone pairs, this is going to be nonpolar, which means the only intermolecular force it can exhibit are London dispersion forces, which is choice D. So covalent bonds, remember, these are not an IMF. Okay, so that holds the atoms together in each molecule, but is not an intermolecular force, that is an intramolecular force. Ionic bonds, this is not an ionic compound, of course. Hydrogen bonds, as we said, the hydrogen would have to be bonded to oxygen, nitrogen, or fluorine. And then finally, this last one, osmotic pressure. That's something you'll learn about in Chem 2, but has nothing to do with intermolecular forces, so we can throw that out and not talk about that anymore for now. Alright, so that takes us to the end of a relatively short review session. We definitely review those concepts if you have trouble with them, read about them, talk to me about them, think about them, do practice problems, whatever it takes to sort of internalize them and really understand them at a deep level. But that'll be it for now, and I will come back with another one next week.